Hi, there is a nice story about the debate between Bohr and Einstein, where actually Einstein got it wrong. So Einstein doubted the uncertainty principle, and in particular the energy-time uncertainty principle that states that delta E, delta T is at least h bar. So what's the meaning of this uncertainty principle? So suppose that you wish to measure the energy difference between two states to a certain accuracy. This uncertainty principle states that you need at least amount of time of delta t larger than h bar over the uncertainty in the energy difference. So Einstein proposed a gedanken experiment where he claimed that he can refute this uncertainty principle, essentially to limit the time to arbitrary accuracy, however small, minimal as one wishes. So that's a very interesting experiment, gedanken experiment, in which Einstein got it wrong. And the interesting thing is that it got it wrong on the GR front. So the problem with the objection of Einstein turned out to be that he missed something in GR in his own theory. And Bohr got it right. So how does it work? So what Einstein proposed is as follows. Suppose that you have a box. This is a box. And you hang the box of, let's say, mass m on a spring in such a way that you know the weight of the box. So it's m times g. And in the box, suppose that there is one photon of mass m and energy, let's say, E small e over c squared. And then, so you know the total mass, let's say m is actually the total mass of both the box and the photon. It doesn't really matter. And suppose that you have a small shutter in this box. So what Einstein said is the following. Suppose that I open the shutter to some time t. Then what I can do, I can control the time of the opening of the shutter. And it could be that during this time, the photon escapes the box. So essentially what Einstein says is that I can measure the amount of energy or mass of the box plus the photon before I open the shutter. And after I close the shutter, and therefore I know the energy difference, if any, between the opening of the shutter and the shutting of the shutter, closing the shutter. So I know the energy of the system to some accuracy, or the mass of the system to some accuracy, delta m, and therefore the energy to an accuracy of delta m c squared. So even if the photon escaped, there is perhaps some uncertainty in the energy of the box plus the photon or not. But the key point is that that doesn't matter. Einstein accepts that any measurement has some limitation to its accuracy. However, what Einstein says is I can control the time of the experiment, the duration of of the experiment to an arbitrary accuracy. So t can be arbitrarily small, and what Einstein claimed is that this t can be less than h bar over delta m c squared. So this is Einstein claim. Einstein claim. Bohr thought about Einstein's gedanken experiment, and he managed to find the loophole. And let me explain what the loophole is. The result, the solution of this paradox by Bohr, how Bohr saved the uncertainty principle. So what Bohr says is as follows. Well, we both accept, he told Einstein, that there is some delta m, because perhaps the photon escaped. So in order to know the energy of the system before and after, we need to do two measurements, one before and one after, and there is some uncertainty in the measurement. Einstein agreed to that. But then what Bohr said is that because of this uncertainty in the, let's say, mass of the box, then there is also some uncertainty in the momentum of the box. And the uncertainty in the momentum of the box is delta P equals delta M times the velocity of the box. Now, what is the vertical velocity of the box? Well, it is g, the Earth acceleration, times t, right? So, because it moves. Right. This uncertainty in the momentum, due to the uncertainty in the mass times the velocity during the motion, slight motion of this box, is delta P. And delta P, according to Heisenberg uncertainty principle, is at least h bar over delta x, where delta x is the vertical motion in the time delta t. So I think that Einstein agreed to that. I mean, Einstein knew and accepted the uncertainty principle that involves momentum and location or position, but he didn't accept the energy-time uncertainty principle, and that's the purpose of this the gedanken experiment. So fine. Now we know that there is both delta x and delta p, and that's fine. And now the key point in this, and this is what Einstein missed, is that due to this uncertainty in delta x, there will be an uncertainty in the time, and as we shall see, this uncertainty in the time saves the energy-time uncertainty relation. So let's see how it works. So let's see what is the uncertainty in the potential energy per unit mass in this story. So this system, we don't know the position of this system to arbitrary accuracy. There is some delta x. As a result, there will be uncertainty in the potential. Let's call it delta phi. Delta phi is the Earth acceleration g times delta x. So this is because acceleration, or well, force is minus the potential, the derivative of the potential with respect to x, then mg is minus dv dx. And if we define phi as the potential per unit mass, then g is delta phi delta x. Right. So here is the interesting part that Einstein forgot, and it's a bit embarrassing because it's about GR. So according to GR, there will be a redshift, or time difference for an observer, from an outside observer, if an object is in different positions in space. So without entering the details of how that is related to the metric and the GR description, let me just say that the uncertainty in the time due to GR is related to the uncertainty in this potential delta phi divided by c squared times t. Of course, in GR, it's classical theory, there is no uncertainty. I mean, in GR, the time difference is the potential difference divided by c squared times the time of the measurement. But the interpretation, or what is relevant to this gedanken experiment, is that we don't know phi to arbitrary accuracy, and therefore it leads to an uncertainty in the time. Then all we need to do is to use the relation between phi and gx. So this is g delta x over speed of light squared times t. So we found the uncertainty in the time in this gedanken experiment, and let's see how much uncertainty we have. So if we multiply delta m that we have times c squared times this delta t, let's see, so we have delta m, and then let's write it this way. This is delta m, and then we have c squared times this delta t. So c squared times delta t is g delta x t. And using this relation, delta mgt is larger than h bar over delta x, then we immediately obtain that this is larger than h bar. So in conclusion, delta E times delta T is at least h bar. So there will be an uncertainty. The conclusion is that there is an uncertainty delta t, which is at least h bar divided by delta E, but this is because we don't know the precise vertical location of this box, and that leads to an uncertainty in the time due to a GR effect. So what Einstein missed is the redshift effect of GR, that there is a time difference, time dilation, or redshift due to the gravitational field. So if an object is at point A or at point B, and there is a different metric or a different potential in space in points A and points B, then time ticks slightly differently for an outside observer, and this tiny difference in the time can be thought of as an uncertainty in time, and that's what saves the energy-time uncertainty principle that Einstein missed, and Bohr got it